Hello AP Physics students, it's Mr. Kennedy. Welcome back to our next lesson in electromagnetic induction. Hope everybody's doing well. Hope everybody's staying safe and healthy. Today we're going to highlight two problems that get at some of the heart of some of Faraday's law, and I'll show you some of those things as we go through, but let's jump right into it. First of all, we saw yesterday that what you would deal with Faraday's law is if you have a changing flux, then the changing flux would produce voltage in a loop of wire. Let's say if you have a changing flux through that loop of wire. And we saw what would happen if the area changed. We saw what would happen if the magnetic field changed. But there's a specific example we want to get to where an area changes. So let's say we have right here a magnetic field going into the page. So there's a magnetic field going into the page. And then we're going to have a wire that's only part of a wire. It's going to be three sections of a wire. So this is a magnetic field going into the page. We'll just call this B. That's the magnetic field. And we're going to have three sections of a wire right here. We're going to have 1, 2, 3 sections of a wire. So, and we'll call this length here L. Now just think of this as bare wire, just a piece of bare wire that's happening through there. And on top of this wire, we're going to put a metal bar. We're going to put a metal bar right here. And that metal bar is going to be able to slide back and forth along here. So just for the sake of argument, we're going to say that we're going to move the this metal bar along this wire at a speed v, at a constant speed v. Right now we'll just call this distance x. That's the distance between this edge and the bar. And the question is, what happens here? What happens, what current flows, what voltage is happening, what's the change in flux? What is really happening with this thing? So when we look at it, first of all, let's look at which direction the current flows, and we'll see why it actually flows that way. So if we look at our right-hand rule, we have magnetic field going into the page, and by moving this bar this direction, we get more magnetic field going into the page. So what we should do is we should make our thumb point up. We should point against the direction that the magnetic field is changing. Curl your hand around, so we should be able to see that the current flows around, in this case, counterclockwise. So we would see that the current flows like this. But there should be another way to verify this, to make sure that it is actually going to flow that way. And one quick way to think about it is, inside this wire, there are going to be positive charges and negative charges. Now, if I took this wire and I brought it to the right, I'm moving this positive charge to the right. Well, if I can see what happens then, I take my right hand, push my charge to the right, fingers are into the page. That means positive charges will move up this way and then along this direction. Now, if you use the rule for the negative charge here, thumb into the page, and then or thumb to the left, fingers into the page, this means negative charge move down. This means that this bar is becoming the voltage source. This bar is becoming effectively the battery for this little circuit that we have here. When you have a piece of wire or metal bar or anything like that moving perpendicular to the magnetic field, then what you create is this becomes the battery. So now we just have to find out what the voltage is on this battery. We've seen that the current flows around this way. It even makes sense with two different right-hand rules. Again, if we point our thumb into the page, it's going higher and higher into the page, so we have to point our thumb out of the page because it's getting bigger through the loop. Curl your hand, and we see this counterclockwise. That's the exact same as I pointed my thumb in the direction that the positive charge moves, and then it forces positive charge to go up. So when you force positive charge to go to the top of the wire and negative charge to go to the bottom of the wire, this is now a voltage source. It's got a positive and negative terminal of this whole thing. So this is going to be a positive voltage source. So But how do we find out how much voltage is actually generated? Well, we can go back to Faraday's law. So Faraday's law says this, that the voltage generated is negative N, the derivative of the flux. But this turns out not to be very difficult because all the pieces here are things we already know. So the voltage then is negative 1. We only have one loop here. We take the derivative of the flux with respect to the area. Well, first of all, the flux points right through the loop, so the cosine is just the cosine of 0, so that's just 1. When we look at the area here, the area doesn't affect the magnetic field. The magnetic field and the area are independent of each other, so this becomes B. The area is X times L. And there you have it. It's negative 1, the derivative of BXL. Well, if you look closely at that, that's going to be negative, B is a constant, L is a constant, so it becomes negative BL dx dt. Now, if you have this, dx dt is just going to be the velocity. That's the velocity that you're moving at. So what you find here is that the voltage that's generated, and I'm going to ignore the negative sign here, is BLV. And that turns out to be something that's very convenient later, because anytime you have some kind of metal bar or even a piece of a wire that's moving, the voltage that's generated is BLV. And the length that you should use is always the one perpendicular to both the velocity and the magnetic field. So look closely here. We don't use this length, we use this length because L is perpendicular to the magnetic field in and perpendicular to the velocity that way. So these three things should be perpendicular and they produce a voltage. So this even happens, for instance, in like an airplane wing. An airplane wing flying through a magnetic field, like the Earth's magnetic field, will produce a voltage across that airplane wing. If you take a metal bar and you wave it around inside the Earth's magnetic field, you will get a voltage generated across that. Might not be very much, but you'll get a voltage generated across that. So again, we saw that by moving this bar, we changed the area, we made the area bigger, and the big thing to get out of this, though, is that the voltage generated will be BLV. This is huge, and it's a big time saver actually on the AP test, because whenever you have like the edge of a wire or anything like that, and you'll see that in some of the problems, that's what you're going to get. So kind of a big lesson that comes out of this type of problem is that BLV. So that's one of those things that I would have in your calculator stored, ready to go, because it's not necessarily something that's given to you on the equation sheet. So I would have that ready to go. But that was the first problem. The big highlight is that the magnetic field, when you have a bar moving through it, produces a voltage through that bar, and this becomes basically a battery. So there's our first problem. The second problem is the first example we have where the magnetic field is dependent on where you are. It is dependent on the area. And for this example, what I'm going to have a wire right here, and this was in some of the conceptual examples we did earlier. There's a wire here, and the current through the wire is going to be I naught e to the negative kt. So this current is changing. It's pointing this direction, but it's changing. And then over here, I'm going to have a loop of wire with certain dimensions on it. It's a rectangular loop of wire. And I will say that it has this side length is A, this side length is B, and it is a distance C from this wire down here. So this is just a loop of wire. There's no current flowing in it yet, but there will be some current flowing in it once we actually start thinking about it. So first thing is, let's figure out which way the current actually flows in this loop of wire. It's going to be induced by this current. Let's see how that happens. If I take my right hand, this current produces a magnetic field that comes up and out through this loop. It comes up and out through the loop. So, because it comes up and out through the loop, I have to ask myself, is this current getting bigger or stronger. And we're going to assume that K is a positive constant. And because there's exponential decay here, the current that's coming out is producing a magnetic field that gets weaker and weaker and weaker. So what does that mean? That means I should point my thumb in the same direction as the magnetic field, so out here, and that means I'll induce a current that flows in this way counterclockwise. So I'll have a current that flows in here counterclockwise. So let's see how we can come up with the amount of current. We'll see what we actually get there, and we'll see what the whole process is. The first part is really about the flux, though. How much flux is going through this loop? That's the sort of the more challenging part that happens here. Well, we know that a wire has a certain magnetic field given by Ampere's law. So if we try to calculate the flux here is going to be the integral of B dot dA. Well, again, this is our first time that we're going to see that the magnetic field and the area actually are linked. And here's why. If I take my hand, point my thumb this way, curl my hand out, each section of this wire is going to have a different magnetic field. A piece that's close here will have a stronger magnetic field. A piece far here will have a weaker magnetic field. So what I do is I break this up. I'm going to break it up. I'm going to take a little tiny piece right here, a representative piece, with thickness dr. So this has thickness dr, which means the area of this little bar right here, this blue bar, the area of that is going to be A times dr. So what I have here is that this is the area. The area is ADR, and I'm going to integrate from all little strips that would go all the way through there, and we'll see what we have. But the magnetic field itself, we know that the magnetic field is going to be mu naught I over 2 pi r. That's the magnetic field that the wire creates. We'll deal with the I part here in a minute because it's really equal to that. The dot product is just going to be 90 degrees because it's going to hit at 90. But then you'll see that I'm going to integrate here over this area. The area is AdR. And I'll integrate. The wire starts at C, at a distance C, and it ends at a distance C plus B. So this is the flux. This is the first time we've seen it where the flux depends on the area. See, this R and this R are actually linked. So the area and magnetic field are linked slightly. Now this is not a really hard integral or anything because almost everything is constant here. So mu naught's a constant. We don't have to worry about integrating I because I is with respect to t. 2 pi is a constant. A is a constant. It's just dr over r. So what we see here is that the flux in this case will turn out to be dr over r. When we integrate that, becomes natural log. So we'll get mu naught I A over 2 pi, the natural log of C plus B over C. So that is the flux. That's the flux that is generated through there. Now, the reality is, though, that there is a time dependence on this flux because I change with respect to time. So I'm going to put that in there next. So flux is really mu naught I naught e to the negative kt over 2 pi natural log of C plus B over C. So this is the flux that happens through that loop. And again, it was the first time we had to see where R and dr, so the area and the magnetic field, were linked in that way. So this is the flux. But we know that a changing flux produces a voltage. So what I do then is I then take that flux and now I use Faraday's law. So Faraday's law says that the voltage generated is negative N times the derivative of the flux. So now I take the derivative of this. The good part about this is everything else is a constant except the e to the negative kt. So all this natural log business is a constant, this is a constant, this is a constant, 2 pi is a constant. So almost everything comes out of this unscathed, and I can take the derivative of e to the negative kt and just be done. So what I get from this is I have negative and then -1, because there's only one loop here. I take the derivative of this, it becomes mu naught I naught. The derivative of e to the negative kt is going to be negative k e to the negative kt divided by 2 pi, and I get the natural log of c plus b over c. And you can simplify that a little bit if you'd like, because the negative signs will just cancel right there. But that's it. This is the voltage generated. So step 1 was find the flux. Step 2 was take the derivative of that flux, and then what you find is the voltage is generated. Now, an additional step that you can take here is once you have the voltage, you can find the current, because if you just use V equals IR, you can take the voltage that you found here, divide by the resistance, and now you have the current as well. So kind of a 3-step process. Step 1, find the flux. Step 2, find the voltage. And then step 3, use V equals IR to find the actual amount of the current. We know that the current flowed this way, but now we know how much it is. Another step that you can take here is to find out what the force between these two wires is. Because if you know that this is a wire pointing this direction and this is a wire pointing this direction, we know that they're actually going to attract toward each other, and these two, this direction and this direction, will actually repel from each other. So now you can actually find the force between them, going back and using something like force equals BIL sine of theta. And this problem, when we were back in class, I would always assign this problem as one of the free response questions on the test. It's really important for one combination of reasons. You can basically throw everything in here with magnetism, electromagnetic induction into one problem. If you notice, you're getting flux in there, you're getting voltage, you're getting current, you're getting forces, you're getting Ohm's law. You can get everything into one. Oh, you can get your other right-hand rules. You're getting all 3 right-hand rules in one problem. So this shows up on the AP test very, very often. It won't show up on this year's test because they're going to cut back on that. But this is a really critical problem to understand because, again, the magnetic field and the area do depend on each other. All right, everybody. Hopefully you can get started on Unit 13, Worksheet 1, problems 4 through 7. Obviously, if you have any questions or problems, feel free to text me or to email me. And hope you have a great day. And don't hesitate to drop me a line if you have any questions that you have. All right, have a great day, everybody.